this course design practice module 9, we were talking about the concurrent engineering philosophy and how to understand this in real practice. So, I had already illustrated this, that the philosophy of engineering design in consultation with all stakeholders associated with the whole life cycle of a product, at the very beginning involving everybody together to emerge the engineering design is called the concurrent concept of engineering design. It is a highly multidisciplinary cross functional approach of designing products, particularly in an environment which is driven by all stakeholders together from the very beginning. And there are a lot of benefits which happen when we talk about such an approach of engineering design, and some of the reasons why concurrent engineering is really the need of the day or need of the hour is that first of all, there is a increased amount of product variety because of customization aspects and demands, almost skyrocketing demands on the part of the consumers about the exact fitting of their needs. And so, therefore, because of the product variety and the associated technical complexity involving a single manufacturing setup, being able to flexibly manufacture in a customized manner, it generally prolongs the development process, because any product which you may envision today and design today based on the manufacturing setup that you already have, with probably very less capital investment and very flexible overall production environment, it is very complex to build such a design, okay, or it is very complex to develop such a product design. So, therefore, because of the product variety and technical complexity, generally the development process gets highly prolonged and more difficult. Okay. So, typically the predictability of what would be the impact of a small design change in the product or maybe a certain design decision on the overall functionality may become increasingly very complex to figure out, and therefore, the performance of the final product sometimes may get jeopardized because of this exodus of customized needs associated with the different markets which are in play and which actually create those forces which are responsible for the realization of engineering products. So, increasing global competitive pressure, that is another reason why concurrent engineering is very important. So, basically the pressure is from the emerging concept of re-engineering of products. Okay. So, you do not know what part of the world what is being manufactured, and that may fall in place with a certain segments wishes or aspirations. And so, in order to map that product, you need to be able to flexibly change everything, including the realization setup, etc., in a very small time, so that you could re-engineer anything which is felt to be the need of the hour and available globally as such on a local basis. The need for rapid response to fast changing consumer demands is again one of the reasons why concurrent engineering should be practiced. Need for shorter product life cycles. Today's products are basically shrinking as far as their life cycle goes, because there is new technology which is emergent, and there is a consumer behavior which is actually geared by an addiction to more and more complexity in the technology. So, therefore, obviously, the product life cycle of certain products have become very, very short, and that is again one of the reasons why the concurrent engineering helps you to go ahead with a psyche of the exact market segment built in the product from the very beginning. So, large organizations with several departments, they work on developing numerous products at the same time. So, if they do it in a concurrent manner, their efforts can be more focused, and obviously, new and innovative technologies emerging at a very high rate, causing new products to be technologically obsolete within a very short period. As I told you about the short life cycle of the product, is another reason why concurrent engineering helps to beat the competition in this kind of a complex environment. So, these are some of the reasons why concurrent engineering is the need of the day. Basically, if I looked at the a characteristic curve which would represent the incurred cost on the product development process as opposed to the committed cost during the whole product life cycle from the conceptual design stage to the detailed design prototype stage, or maybe the manufacturing and the post manufacturing distribution, service and disposal stage. So, let us look at this curve behavior, how what are the different costs. So, at the planning and design stage, of course, there is going to be research and development cost and cost of product design, etc., which is going to be the bulk of the committed cost. And in fact, if you commit this cost, as you can see, the total amount of cost that is actually incurred in the conceptual design phase actually falls down as a percentage, because and then it actually also gives you a very smooth rise all the way to the manufacturing phase, because you have involved a lot of investment in the design itself of a product. Then of course, there is a manufacturing phase where the stage witnesses a sort of growth and maturity in the sales, and all the manufacturing, marketing, selling and distribution costs are incurred at this particular phase, and that is one of the reasons why there is a sort of a rise, a gradual rise in this particular phase of the actual cost incurred. And then there is a service and abandonment stage, and this is typically the last stage of the product, where it is all post distribution and in the market. So, at this stage the product life cycle is signified by a decline in the sales volume. So, the demand for the product declines at this stage. On the other hand, the producers may be required to provide a sort of after sales service and already sold products, and there are costs incurred, various costs incurred at this stage, okay, which kind of plateaus down, because of the a certain level of constancy in the size of the market. Okay. So, that is how the cost incurred goes, and this kind of shows what is the committed cost. Okay. So, most of the committed cost, about almost 80% is actually at the design stage of any product, beyond which it kind of determines what is the cost that would be involved in the manufacturing. So, if you are investing more amount of money in the design phase, typically it kind of leads to a quick constancy in the overall committed cost plan that is associated with the product. So, this is a sort of a curve which signifies what are the various aspects related to the actual commitments of the cost being made and the costs that are being incurred, the various stages of design and manufacturing and abandonment or distribution or sales service phase of a product life cycle. So, there are some results that I would like to share of a survey, which includes an improvement to specific product lines by application of concurrent engineering philosophy. There are various concerns or companies which are involved in showing such a reduction, and you will get to know from these statistics that I am sharing with you how important the concurrent philosophy of engineering design can be in terms of overall improvement in product lines. So, when we talk about development and production lead times, product development time has been shown to reduce almost up to 60% with the concurrent engineering philosophy being implemented, and the production spans have reduced by almost 10%. So, if we looked at in specifics related to certain companies, AT&T for example, reduced the total process time for the ESS programmed digital switch manufactured by them by almost 46% in a 3 years time phase using concurrent engineering philosophy. Similarly, John Deere reduced product development time for construction equipments by almost 60%, again using the concurrent engineering philosophy. There are other companies like ITT for example, which reduced the design cycle for an electronic countermeasures system by almost 33%, and its transition to the production time by almost 22% again by utilization of the concurrent engineering philosophy. So, there are numerous such examples in terms of measurable quality improvements, in terms of engineering process improvements and overall cost reduction, where a lot of concerns have shown, a lot of companies have shown reduction in the overall cost or increase in overall process improvement through concurrent engineering philosophy. For example, if you looked at quality improvement, almost yield improvements to the level of almost up to 4 times have been recorded. Field failures, for example, reduce up to 83% by in case of AT&T, which achieved almost a 4-fold reduction in variability in a polysilicon deposition process, okay, on a microchip production line for very large scale integrated circuits, typically also known as VLSI circuits. And it also achieved nearly 2 orders of magnitude reduction in the surface defects associated with such polysilicon deposits, because of the utilization of the concurrent engineering philosophy with involvement of everybody. Similarly, in the ESS program, digital switch manufactured by AT&T again, which is actually known to be a company which is quite conversant with this implementation of the concurrent engineering approach. They reduced defects to almost about 87% through a coordinated QIP that included product and process design improvements being suggested by a team of professionals working in a concurrent manner. Similarly, John Deere reduced the number of inspectors on their production lines by almost 2/3 through emphasis on process control and linking design and manufacturing processes closely, so that they could have measurable quality improvement again as results because of the concurrent engineering applications. There are other examples also for engineering process improvement. For example, engineering changes per drawing have been seen to reduce almost 15 times sometimes. Early production engineering changes got reduced by about 15%. Inventory items stocked and essentially blocked capital reduced to almost 60% by use of a concurrent engineering philosophy, just because there was a stakeholding from all associated people with a product development or manufacturing or even sales and service process, or let us say associated with the whole product life cycle of a product. Again, engineering prototype builds reduced by almost up to 3 times. If a certain number of iterative prototypes were planned with the serial engineering, with the concurrent engineering, it probably could be accomplished by almost 1/3 of the numbers that was there in the serial engineering approach. Scrap and rework reduced almost up to 87% because of concurrent engineering philosophy again. If we talk about cost reduction, again the famous McDonnell Douglas airplanes manufacturer had a 60% reduction in life cycle cost, almost a 40% reduction in production cost, particularly on a defense program related to missiles. Again, Boeing reduced a bit on a mobile missile launcher, realized the cost almost about 30 to 40% below the bidded price, just by applying the concurrent approach in their overall philosophy. Similarly, IBM could reduce direct costs and system assemblies by almost 50%, or ITT saved about 25% in the ferrite core bonding production costs by using concurrent engineering. So, there are numerous examples cited in literature where you see how important it is to design with a concurrent philosophy. Okay. So, we will now like to investigate a small model based problem. It is a case study of a company which requires about 1000 units of turned cylindrical part to be produced. A shaft needs to be produced on a turning machine. Okay. And the design department of this company defines a need for a cylindrical part to be finished to an extent of about 1 plus minus 0.003 inches. That means, the overall dia of this part or diameter of this part varies between, or as acceptable limits between 0.997 inches on one side and 1.003 inches on another side. So, here the idea is to use first the serial engineering approach to see what is going to be the overall cost per piece in order to bring out this through the process of the design and the manufacturing improvement, and then using a concurrent engineering solution in another scenario, and then there can be a cost comparative drawn in terms of the final produced product being manufactured. So, you will see how this concurrent engineering philosophy as applied to a sequential, otherwise a standard sequential engineering activity can bring down costs significantly of the pieces which have been produced through this approach. So, I will just highlight what the serial engineering approach had to face as challenges and what the concurrent engineering approach had to face, and then we will work on developing a mathematical model to understand how the cost can be optimized to the best possible value through both the approaches. So, in the serial engineering approach, the design department of this company recommends a overall shaft dimension and tolerance in the range of 1 plus minus 0.003 inches, and this information is transmitted to manufacturing engineering. And obviously, in this particular serial engineering approach, the manufacturing engineering accepts these specifications, tries to attempt to build the part, tries to find out the best manufacturing technology that they may have to accommodate the request made, and they can only challenge the specification as set up by the design department if the design is not compatible and producible in one of the machines which they may be having. And so, drawing on the preceding analysis, the manufacturing engineering decides in this particular case to produce the parts, and it uses a turret lathe which is there already with the manufacturing engineering department, because whatever tolerances have been desired by the design can be easily implemented. The process average and the standard deviation of the turret lathe that is there with the manufacturing engineering happens to be about 1 inch, and it also happens to be the deviation happens to be about 0.003 inches. So, there is a good match between what needs to be produced and what has to be delivered, but essentially this may not be all the information that is needed to finally calculate what is going to be the cost related to such a product, because the question that may be asked is whether really we need this kind of a close tolerance in the finish, and that can be best adjusted by a person who works, let us say in the post sales service, which talks about what is going to be the reliability aspect, or what is going to be the warranty failure, or what is going to be the cost associated with such failures, what is the criteria of the failure, and also the quality person who is in house and working on a problem and tries to implement this particular specification within an engineering assembly. So, from his learning somehow the overall need statement which came up to the design department can get influenced, and therefore, there may be a much broader specification range in which the piece can be turned and produced at a much lower cost, because it may not be necessary that the tight tolerances given by the design are really the ones which are required by the whole process. So, we will slightly change the connotation when it comes to a concurrent engineering approach, and there will be various issues which need to be addressed by again CFTs or cross functional teams in this particular case. For example, the marketing services for this company finds that the tolerance range 1 plus minus 0.003 inches may be too tight, and it is really not needed. I mean, you can work with a better specification, a much wider specification, where process control of that level may not be really needed. The quality department, however, did not like the number of rejections, because obviously if there is a process in place and there is going to be some feedstock given to the process and it produces some output, there are going to be rejects. And so, if the process capability of a machine is not very well defined, then obviously there may be rejects and costs related to the rejects. So, we need to build a mathematical model around all this to approach this problem, so that we can actually bring the specifics of the cost. We will make some assumptions about the different costs related to the raw materials, or that related to the rejected materials, or that related to the material which comes out, and then we will finally try to do both the philosophies in place and try to calculate what is the overall cost. Similarly, in the concurrent case, the manufacturing planning department, it wants to use machine tools with better process capabilities, so that they can work on closer tolerances, but this is a conflicting interest with the marketing, which says that the tolerance range given is too tight and it may not be necessary really for the product. and similarly the purchasing department cannot buy so many raw shafts because of the restricted availability of such steels. So, they would also look at what quality is saying in this particular case about lower number of rejects. So, it is some conflicts which are there at the very beginning, and if they can be involved at the outset, the design which will emerge will be making everybody else happy about their requirements, and then that the goals of an organization to design something in concurrence, okay, with everybody who is a stakeholder would be the best possible alternative in this kind of a conflicting situation. In the serial approach, if we had introduced this design specification, there would be checks and balances at every stage, and it needs to iterate probably many times before the final design can come through. Whereas, in the concurrent, you can do one shot with all opinions together and make a design which may not need to be prototyped for more than one, probably for more than 1 or 2 times. Probably a prototyping for a second time may be needed because of some functional aspect associated with the product, as we will find out later, okay, which may get emerged in the concurrent engineering case. So, let us look at how we will develop a process model for this. So, in this particular case, we consider a very simple product, that is a cylindrical shaft, and at the design stage we are concerned with specifying the tolerances on the shaft, which has already been done to be 1 plus minus 0.003 inches. And the manufacturing stage, again it is sort of a transformation process, that whatever raw material we have in terms of rods or feedstocks which we are giving to the system, they would like to turn the rod into a smaller diameter rod. So, a bar stock, for example, would be converted into a finished shaft meeting the necessary tolerance specifications as specified by the initial design. Okay. And the transformation process would indicate inputs and outputs in the following manner. So, let us say this circle here represents the transformation method, and there is some kind of a input material which is given to a transformation process, and it generates an output material. So, obviously, such a transformation would also be responsible for generating many process rejects, because it may not fully comply to the tolerance specifications indicated. The capability of the process may be lower in comparison to the tight tolerances which are being specified by the design, and therefore, there may be some cases where there are non conforming parts, or parts not meeting specification. So, we would like to sort of look at it from the standpoint of a normal distribution, where we have a process mean and a sort of an average standard deviation, and as you know that such distributions are signified by a inverted bell shaped curve as is represented here, and this is the process mean around which this curve is centered. So, the normal distribution function is typically represented through 1 by root of. So, this is the standard normal distribution function. So, 1 by root of 2 pi times of e to the power of minus t square by 2, I am sorry, this is x. Okay. So, minus x square by 2, and in fact, if I wanted to see what is the area under this curve, and also the area under the curve is of more important significance when you typically do a scaled normal distribution with 1 by sigma or 1 by standard deviation in place for the whole function here. So, the cumulative density function CDF, which signifies the area under the curve here, would be represented then by 1 by root of 2 pi with t varying between minus infinity to the value z e to the power of minus t square by 2 dt, where z typically is the scaled variable, which is actually the x minus the mean for the process, okay, divided by the sigma for the process. So, that is how you scale the distribution, the standard normal distribution, and obtain the area under the curve. So, having said that, and this is all very commonly available information as far as statistical process control goes, I am just going to apply this to the concurrent engineering philosophy that we are talking about when we mention about this as an engineering design tool. So, here there are going to be upper specifications and lower specifications given by the design department, which have to be overlapped with this process characterization or process characteristics of a mean and a variance which is related to a certain process. So, for example, if the process is a turret lathe which has been seen here, the turret lathe in question may have a certain capability in terms of giving a certain mean dimension and a certain variation in production of parts. And so, that mean and standard deviation would then be the process mean and the process standard deviation, which we have to overlay on the design requirement, which is the upper and the lower specification given by the design department. Remember, it was given as 1 plus 0.003 inches on one side and 1 minus 0.003 inches on another side. So, supposing let us say the design department specifies a tolerance limit corresponding to the kth alternative system of tolerances that the whole engineering assembly has, and there is an upper side of the tolerance and then there is a lower side of the tolerance that has been specified. And let us say, so this is corresponding to the kth alternative system of tolerances, and let us say we are evaluating J machines in place which are there in with the manufacturing wing, and all these J machines would have different process capabilities. And when we talk about the jth machine that we want to mix and match, for example, in this case the turret lathe may be the such a machine, such so we just number them what we have as different processes. So, the jth machine's capability is illustrated in terms of a process mean and a process standard deviation, let us call it mu j and sigma j. So, then in this case the scaled variable that we are talking about for this building up this cumulative distribution function, which is otherwise actually the scaled variable, if we look at here the CDF corresponding to the whole area under the curve varying from minus infinity to z equal to plus infinity happens to be unity. Okay. So, that is how, so it is like more like a 100% of the parts qualify to lie within that distribution when we go from minus infinity to plus infinity of the scaled variable. So, the scaled variable in this particular case for overlapping the tolerance or overlaying the tolerance on our process capability for the jth machining system is given through an upper scaled variable and a lower scaled variable. So, the upper scaled variable is nothing but the tolerance given the kth tolerance which is being manufactured on the jth machine which has capabilities mu j and sigma j, and similarly there is a lower scaled variable based on the lower tolerance given on the same machine, the jth alternative machine which has mu j and sigma j as the process mean and the process standard deviation. So, these are the standard normal variates, okay, and these are very important because such scaled variates would get into such a distribution function here as shown here, which corresponds to 100% inclusion of whatever parts are being produced, okay, to fall under the whole normal distribution curve as mentioned here. So, let us now look at some numbers in terms of number of inputs and number of outputs and see how the input output behavior or flow would happen in this particular case. So, let y 0 j k and y I j k and y s j k signify the output coming out here in this particular figure, the input which is being fed inside the figure, and the scrap or the rework or the rejects which are coming out as a result of this transformation matrix. Okay. So, let us say this kind of simplifies the analysis that anything above the lower tolerance or below the anything below the lower tolerance or above the upper tolerance are sort of rejected together, and we look at this stage to the fraction of scrap that is generated. Okay. So, the we call it the scrap the fraction of the scrap as SCJK, and this SCJK is nothing but the percentage scrap units per unit or the number of scrap units per unit the number of inputs. So, basically it is about how much of material is actually not getting transformed and being sent out by the transformation process as scrap. So, if I looked at again the normal distribution and the way that rejects are being done, you know that there is a process mean, and obviously there is a upper tolerance and lower tolerance corresponding to which there is a z variate which has been plotted. So, there is a z variate lower and z variate upper. So, this is corresponding to let us say the upper specification limit of the kth specification system and the lower specification limit of the kth specification system. So, everything which falls outside this domain, that means the shaded area represented here, and everything which falls outside this domain would correspond to, let me just shade this in a little different manner, so that it is better for us to understand. So, let us say this is shaded in this manner. Everything falling above the upper specification or below the lower specification this way are being rejected, and everything which is actually in between here qualifies to the design specs are being accepted. So, we know that in this particular distribution, because it is a scale distribution and 100% components correspond to the value 1, which is the area under the curve. So, I would say that 1 is basically a summation of all these different areas. So, you have an area shaded like this, you have an area shaded like this, and then again an area shaded in this manner. So, these are sort of cumulatively all these areas together mean that 100% lie within this particular zone. However, out of this 100%, these two are the areas which would be needed or which would need to be taken off from the cumulative distribution function which we had earlier provided in the last slide, in which we talked about 1 by root of 2 pi integral minus infinity to z e to the power of minus t square by 2 dt, this value of the integral or area under the curve, when the z here is a distribution x minus mu by sigma. So, a scaled distribution. So, obviously, we can find out the values of this numerical integral and record these, and these are also available as standard tables from which we can find out what is the percentage which is being rejected on either side of the upper and lower specification limits. So, for example, if I wanted to find out what is the rejects above the upper tolerance limit in this case, I would look at the whole distribution as 1 and just simply subtract the numerical integral 1 by root of 2 pi integral varying between minus infinity to the point z here, okay, e to the power of minus t square by 2 dt. So, the area under the curve corresponding to these two values would have to be subtracted from 1 in order to get this particular value. So, this corresponds to percentage rejects failing the upper specification limit. Similarly, so I call this 1 minus phi of z u j k. Remember, we are representing this function through a function phi of the variable here z. In this case, it is z upper, okay, while choosing the kth specification and trying to process it through the jth machine. Okay. Similarly, I would like to get a value on this side of the normal distribution, which is actually 1 by root of 2 pi, again varying between minus infinity all the way to this value z here, which is z lower j k e to the power of minus t square by 2 dt. So, this is another numerical value that I would like to get from the normal distribution. I call this value as such phi of z l j k. So, if I add the phi of z l j k to the 1 minus phi of z u j k, this is typically what we are talking about as the total percentage rejects failing both the specification limits, both the specification limits. So, that is how we try to analyze the total percentage rejects in this particular case or category. And the idea is that once we get this value estimated from a simple normal table, I should be able to put this in terms of cost calculation, which I will probably do in the next lecture. So, thank you very much for being with us here, and in the next lecture I will show you how the overall cost gets influenced because of this many percentage of rejects, which gets generated because of force fitting a certain specification limit on a process capability associated with the machine. Thank you very much again.